Hello, everyone. In the last video, we discussed the theory and origin of finite element methods and the definition of Cauchy stress tensor in incompressible flow. We also completed the derivation of dimensionless form of incompressible Navier-Stokes equation. Today, we will continue our discussion on Petrov-Galerkin finite element formulation for incompressible flow. Specifically, we will start formulating the Galerkin finite element terms in the Petrov-Galerkin formulation of incompressible flow. From the last video, we have derived the dimensionless form of the governing equations of incompressible flow. We introduced the modified pressure term to combine the pressure term and gravitational term together. The modified pressure is commonly used in the Navier-Stokes equation in single-phase flow. Before formulating the Petrov-Galerkin finite element formulation, we want to simplify the symbols of dimensionless terms by dropping out the asterisk superscription and represent the modified pressure as lowercase p instead of the capital letter P. We may find that the vector, matrix, and tensor are usually represented using bold letters in technical book or academic research papers. Nonetheless, here, we use a more distinction way to differentiate them from the scalar term, as shown at the bottom of this page. Here, we also use uppercase phi to represent the test function basis vector and the lowercase phi to represent the trial function basis vector. So next, we know that the solution to finite element formulation are solved in linear algebra system via matrix and vector operations. The next question to us is that how can we write the weak form in its matrix form and put it into a computer code to solve for it? To understand this process, let us look at it from the theory of finite element methods. In the last video, we already know that the finite element methods can be considered from different perspectives. One of those is that finite element method is in fact a series of projection operations from infinite high-dimensional functional space on a finite lower-dimensional function space. These projection operations are completed via the matrix vector multiplications of test and trial function basis vectors. You will realize that each row of the finite element matrix refers to the computation related to one of the test function term, and each column of the finite element matrix refers to the computational related to one of the trial function term too. In other words, the finite element mass and stiffness matrices are considered as the inner product like projection operators in temporal and spatial spaces, respectively. Therefore, for instance, we look at our fluid mechanics problem. We have 3 components of velocity terms and 1 pressure term. Totally, we have 4 components in our computation. So the rank of the local elemental finite element matrices are 4, as shown on this page. If we look at each term in these elemental finite element matrices, it is very clear that these are the inner product of the test and trial function vectors. For instance, the matrix term at the first row and the second column is associated with the x component of velocity test function and the y component of velocity trial function. Therefore, we can write the elemental mass and stiffness matrices and the elemental force vector into their block form. In each block, the rank of this matrix block depends on the type of element used in calculation. For instance, for a 3-dimensional hexahedral element, the rank of these matrix blocks is 8. Hence, the rank of elemental mass and stiffness matrices is 32 in this case. In Petrov-Galerkin finite element formulation, for the purpose of clarity, we conveniently separate the finite element matrices into their Galerkin and stabilization components. You can see this from the subscripts of the mass and stiffness matrices on this page. In this video, we first assemble the Galerkin terms of elemental mass and stiffness matrices. In the next video, we will talk about how to formulate the stabilization components into their matrix form and assemble the elemental matrices and vectors into the global mass and stiffness matrices and global force vector. Okay, now let us discuss the Galerkin terms for the weak form of conservation of mass. As shown at the bottom of this page, we first formulate the weak form of conservation of mass based on the weighted residual method in finite element formulation. After that, we write this weak form into its component form. Based on our previous discussion, we know that the multiplication of the pressure test function and the x-directional derivative of x-component velocity should contribute to the matrix block K41. Therefore, we can write its spatial integral into the matrix block K41. Similarly, we know that the multiplication of the pressure test function and y-component velocity derivative should contribute to the matrix block K42. Again, the integral of multiplication of phi p and z-component derivative should be written into the matrix block K43 as well. The Galerkin finite element formulation for the weak form of conservation of mass is very simple. Now, let us look at the weak form of x-component of Navier-Stokes equation, as shown on the top of this page. The first problem we encountered is that the diffusion term contains the second-order derivatives of velocity. We remember that the governing equation is solved in its weak sense in finite element methods. This is achieved by applying the technique of integration by parts on the higher-order derivative terms, so the order of derivatives are equal in both the test and trial function spaces. The side effect of applying the integration by parts technique is that we have a boundary integral term, which is related to the traction along the boundary of the fluid elements. In finite element syntax, we call these traction variables as secondary variables. The secondary variables are different from the primary variables. The primary variables refer to what we are solving for in a weak formulation. This is why we usually see the term Navier-Stokes equation in its primary variables, whereas the secondary variables are quantities derived from the primary variables through constitutive relations or differential operators. They are not solved directly and usually computed after obtaining the primary variable field. For instance, the secondary variables are usually needed for post-processing, like stresses, fluxes, gradients along a surface, which are usually computed in boundary integrals. The next problem we encountered in the weak form of Navier-Stokes equation is the nonlinear advection term. In order to solve this weak form in linear algebra system, we need to linearize this nonlinear advection term. To do that, we may use pictured linearization technique and solve for the primary variables over loops of iteration. This is the simplest form of linearization, in which we replace one or some of the primary unknown using the solution we obtained in the last iteration. However, the pictured linearization technique only has linear convergence, and it is too slow to achieve the final solution. To achieve the quadratic convergence speed, we apply Newton linearization technique in this video. Therefore, the linearized weak form of x-component of Navier-Stokes equation can be written in the form shown in the red box, in which the terms related to Newton linearization is highlighted with red color. The derivation of Newton linearization process for the nonlinear advection term is relatively straightforward. We first write the true solution as a linear combination of the solution from the last iteration and a correction term, delta u. We substitute this representation of velocity into the nonlinear advection term and completely expand them into multiple terms. In Newton linearization, we neglect the higher-order quadratic term, since it has much weaker influence to the other terms in the correction process. Finally, we substitute the correction term, delta u, based on our defined representation of velocity. We can write the linearized advection term as shown at the bottom of this page. After the integration by parts and Newton linearization, we can combine some of the similar terms to form the Galerkin finite element formulation of x-component Navier-Stokes equation, in which the terms related to Newton linearization are highlighted in red color. We move all the matrix terms to the left of the equation and move the vector terms to the right of the equation. Finally, we can also define our x-component of fluid stress exerted along the solid surface as tau x, as shown at the bottom of this page. Now, we can rearrange these terms into different matrix blocks, based on their contributions to the corresponding terms in the test and the trial function respectively. For examples, the terms containing the x-component of velocity test function and the x-component of velocity trial function are added into the matrix block K11. Among these terms, the traction term needs special consideration. In the classic finite element formulation, the value of primary variables are identical, although their derivative across these element edges are discontinuous. The exception could be the discontinuous Galerkin finite element formulation. Okay, we come back to the Petrov-Galerkin finite element method based on the classic finite element assumptions. Consequently, in our Petrov-Galerkin formulation, the boundary integral of traction terms between the two neighboring elements sharing the same edge will be cancelled, since their outward normal vectors of these elements are pointing to the opposite direction. On the contrary, if this element's edge is along the boundary of the global computational domain, we will need to specify either a Dirichlet boundary condition or Newman boundary condition. If this boundary is imposed by a traction-free boundary condition, we can just simply neglect the boundary integral of the traction term. If we want to impose a Newman boundary condition along this edge, we can specify a particular value for this traction term and evaluate this boundary integral in the force vector. On the other hand, we may also want to impose a Dirichlet boundary condition along this edge. In this case, we can neglect the boundary integral along this edge as well. It is also noteworthy that we can only impose either a Dirichlet or Newman boundary condition along a boundary, but not both. You may be heard about Robin boundary condition, which is a linear combination of a fixed value of primary variable and its flux along the boundary, but this cannot be simply considered as imposing Dirichlet and Newman boundary conditions together. You should be clear about this in mind. Since it is out of the scope of our video, we will not go deeper into this matter in this video. So now, we have derived the final matrix form of the Galerkin terms in Petrov-Galerkin finite element formulation for X component of Navier-Stokes equation. Okay, now following the same derivation, we can arrive at the final matrix form of the Galerkin terms of Petrov-Galerkin finite element formulation for Y component of Navier-Stokes equation, as shown in the red box on this page. Following that, the matrix form of the Galerkin terms of Petrov-Galerkin finite element formulation for the Y component of Navier-Stokes equation can be shown here in the red box on this page. Now, we have completed the derivation for all the Galerkin terms of the conservation of mass and three components of Navier-Stokes equation for incompressible flow, together with their stress components in three directions. In the next video, we will talk about the stabilization terms in Petrov-Galerkin finite element formulation and the choice of time integrations for the transient problem.